Let's start a discussion about how research is actually conducted. One possibility is to study individual variables. In this case, a variable could be observed, and then statistics could be used to describe and or categorize the variables that were observed. A more likely scenario, though, is that research is used to describe relationships between variables. So two or more variables are observed and measured, and in this instance, we'd have to use at least one of two possible data structures to determine what is the nature of the relationship that exists between them. The first possible way of examining relationships between variables is what the book calls data structure 1, that is the correlational method. The correlational method examines one group of participants whom it measures on two variables. So nothing is manipulated, nothing is changed. It simply measures the natural occurrence of two variables, each within the same participant. The goal is to describe the type or direction and the magnitude or strength of the relationship. It's very good at showing patterns of relationships between variables, but it's non-experimental. That is, it cannot tell you what caused what or why something happened. So there's two things that you need to pay attention to with a correlation. Write this down, it's really important. First is the number. The number is going to appear somewhere between 0 and 1, the numeric value of the correlation. And that's going to tell you the strength or the magnitude of the relationship between the two variables. So a correlation of 1 means a perfect correlation or the strongest possible relationship. Correlation of 0 means there's no relationship whatsoever between the two variables. The second thing you need to be aware of is the sign, that is the positive or the negative attached to the numeric value of the correlation. A positive correlation means that the values move in the same direction. So as one value increases, so too does the value of the other variable also increase. Take height and weight, for example. As a person tends to get taller, they also tend to weigh more. So as the two variables increase together or they decrease together, that's a positive correlation. A negative correlation, on the other hand, means that the values move in the opposite direction. So as one value increases, the other value tends to decrease. So take, for example, amount of hours slept and fatigue. The more hours you sleep, that is that variable increasing, the less fatigue you tend to feel, that is that value decreasing. Don't get confused and see a negative sign on a correlation and think that it means both values are decreasing. Remember, the negative is telling you the direction or the type of relationship, whereas the sign is telling you the magnitude or the strength of the relationship. Here are a couple graphics depicting the correlation. In frame A, you can see that several students participated in this study. We labeled them A through H. We measured them on two variables, wake-up time and academic performance. Nothing was manipulated, nothing was changed. We simply observed two values for each student and recorded them. We asked them what time they woke up, and then we measured their GPA. In frame B, a graphic called a scatter plot is depicted here. The scatter plot's a really important way of understanding the correlation. First, look at the horizontal or the x-axis. You'll see wake-up time is plotted there, 7, 8, 9, 10, 11, 12. On the vertical or the y-axis, we've plotted the other variable. In this case, it's academic performance. Each one of those dots represents one of the students, A through H. So student A, for example, is that second to last dot from the right. If you move over to the 11 and then up to 2.4, you will see he is represented by that piece of data there. What's depicted here is a negative correlation. It's reasonably easy to see that the earlier one gets up, the higher their academic performance is. So as wake-up time increases, academic performance decreases. As wake-up time increases, academic performance decreases. It's a negative correlation in this case. There are limits to the utility of a correlational method, however. It's incredibly good at demonstrating the existence of a relationship, but it cannot provide an explanation for that relationship, and most importantly, it cannot demonstrate a causal relationship. That is, it can't tell you what caused what. There's at least two reasons that the correlation. A second possibility for comparing the relationships between variables is data structure 2, in which we can compare two or more groups of scores. In this example, one variable defines the groups, and a second variable is used to measure the groups. You can do this in either an experimental or a non-experimental way, both of which we'll talk about in the very near future. Here's an example of data structure 2. In a study, a classroom of school children was divided into two groups. One group saw a 30-minute video that contained acts of cartoon violence. The other group saw a different 30-minute video that was a cartoon comedy and contained no acts of violence. Then, when the children were at recess, their behavior was observed and coded for instances of aggressive behavior. So in this instance, the first variable defines the groups. That is, some kids watched a violence video, other kids watched a no violence video. The second variable, the number of aggressive activities or behaviors that they displayed on the playground, was used to measure their behavior. And so those scores that you see in the graph are the number of aggressive behaviors that were coded as the kids were playing on the playground. These scores are used to compare the two groups. To demonstrate a cause and effect relationship between two or more variables, one has to use the experimental method. It's the only way it can be done. To conduct a true experiment, at least two factors have to be taken into consideration. One is the issue of manipulation. That is, the experimenter has to control one variable and determine which participants get which type of the variable or which level of the variable. The other thing that has to be taken into consideration is the issue of control. That is, we have to rule out the influence of all other variables, characteristics of the participants themselves or characteristics of the environment or the situation in which the experiment was done. In other words, we have to know that the two groups of participants were effectively exactly the same other than the one variable which we manipulated. That way, any differences which emerge between the two groups must logically be due to the one thing that was different, and that is the variable we manipulated. This is some incredibly important terminology about experimentation. Independent variable is often abbreviated IV, and dependent variable is often abbreviated DV. So the independent variable is the variable that the experimenter manipulates. It is, in effect, the cause side of the equation. The dependent variable is the one that's observed or that's measured by the experimenter. This is the one that is expected to change. This is the cause side. So if there's a difference between the two groups, it's expected to occur because of the independent variable, and the difference will be manifested or reflected in the values of the dependent variable. This is an example of an experiment which I always think is sort of funny. So variable 1 is the independent variable. Some participants are brought into the lab and asked to count actual money, whereas other participants are brought into the lab and asked to count sheets of green paper that are cut to be about the same shape and size as money. And then afterwards, all participants are tested by placing one hand in a bowl of hot water and then rating the pain level. So what you see for the dependent variable are those numbers in the chart. Those are each person's pain ratings after having counted money or having counted paper. And then we'll compare those two groups on their pain ratings. So any difference between the ratings between the two groups is attributed to the independent variable, that is, having counted paper versus money. And if you look at the scores, you can see that even brief exposure to a whole bunch of money makes us more resilient to a little bit of pain, it seems. There are various methods for ensuring experimental control. One is random assignment. Random assignment is a way of making sure that every subject is equally likely to be in any condition in the experiment, or that every member of the population is equally likely to be in any condition of the experiment. So in our study of women's sleeping habits, we wouldn't want to recruit all of our participants from the sorority houses at the University of Arkansas, because those women are not randomly chosen and they're not necessarily representative of the broader population. Matching subjects may be done as well. So perhaps we think that gender affects aggressiveness. So in our study of the violence or no violence video, we could match subjects by making sure that there's an equal number of boys in the violence condition and in the no violence condition. Or we could hold the value constant and only study boys, make sure that we had all boys in the violence condition and all boys in the no violence condition, and in that way there could be no effect of gender because only boys were included. Separate but closely related issue is the control versus the experimental condition. The experimental condition are the people who do receive the experimental treatment. So those children who did see the violence video and those adults who did actually get to count money. The control condition are the people who do not receive the experimental treatment. So the kids who watched the comedy video or the adults who counted the paper. And they are there as a baseline. They are there to receive no experimental treatment other than the effects of having participated in an experiment at all, to provide a comparison for the experimental condition. This is the issue of a placebo. You guys know what a placebo effect is. It's an effect that emerges because a person was just in an experiment. So the control condition there is in place to provide a neutral baseline for comparison against whatever the effect of the experimental condition is. You can use data structure too in a non-experimental method. So this is any method in which random assignment hasn't occurred or manipulation of a variable hasn't occurred. There are some obvious examples when this happens. One is the non-equivalent group. So a researcher just compares groups of subjects that are different from each other. So if we want to compare men and women, for instance, nobody's going to randomly assign anybody to be a man or to be a woman. We can't control who goes into which group. They're simply non-equivalent groups. Secondarily, there's also the pre-test, post-test design, and this is when the same people are measured at 2 times. So we may look at reading ability of a group of students in 3rd grade and then reading ability of the same group of students in 6th grade. The researcher didn't control the passage of time, but in either instance, the passage of time or the gender, that variable was used to define the group. It looks like an independent variable, but it wasn't manipulated by the researcher. And so in this case, it's called a quasi-independent variable. And this research is also called quasi-experimental in many instances. You may see that term. It just means one variable that wasn't manipulated by the experimenter was used to define the groups. Let's do a couple questions to make sure we're all on the same page. Researchers observed that students' exam scores were higher the more they slept the night before. This study is an example of, what do you think? Of course, D is correct. This is a correlational study. 2 variables were observed: the amount of time students slept the night before and their exam score. Nobody was awakened at any particular time, so no variable was manipulated. We simply measured the natural occurrence of 2 variables and looked for a relationship between the 2. Let's try a true and false. All research methods have an independent variable. What do you think? Sure, good job. That's false. All research methods don't have an independent variable because the correlational method doesn't need an independent variable. It just measures two naturally occurring variables and looks for a relationship. Last one in this section. All research methods can show a cause and effect relationship. True or false? What do you think? That one's false as well, because only experiments control the influence of all factors, participant factors and environmental factors. So only the experimental method has control and manipulation, and those are required characteristics for cause and effect relationships. So only the experimental method can do that.